Good morning, everybody. Today we have with us Eric Weischaufs. I'll give you a little introduction about him. Eric started his career as a graduate student in Yale, and then he became an independent scientist and joined EMBL. In 1981, he moved to Princeton University, where he works on embryonic development of Drosophila. Eric, along with Edward Lewis and Christian Nielsen-Walhard, was awarded the Nobel Prize in Medicine in 1995 for their discoveries concerning genetic control of early embryonic development. So without further ado, let's welcome Eric Weischaufs. Hello, Professor Weischaufs. Thank you for joining us today.
It's good to be here.
Right. So just to start off, can you tell us something about your journey and with different phases as a student, as a researcher, and as a teacher?
So as a student, I think it's true for most students, you don't really know for sure what you want to do with your life. As a young student, I thought I wanted to be an artist. I had the opportunity to go to a science camp when I was 17 and discovered science. And I think, in a certain sense, the rest of my career has been an effort, in a way, to combine science with my early artistic tendencies. That's an interesting thing to say, because you could look at my career and you could say, I'm 100% a scientist and not an artist at all, but I still feel that me as a scientist I've relied heavily on visual aspects of the phenomena that we study in the lab. And it's of course true that embryos and embryonic development is a very visual process. Right. Cells move, cells change shape. The relevant things are things that you can see and that you can understand by seeing. And that's what attracts me to work on embryos.
Right. You were at Notre Dame and you were at a biology major, and then you joined Harvey Bender's lab.
Yeah.
And those times were a little troubling, I suppose, because of the Vietnam War.
Yes.
Can you tell us a little about your experience in the lab and how was it?
So it was important for me to, I needed money, actually, so I had to work in a lab making fly fluid and washing bottles. But that was a good experience in that it taught me something. I used to think that from textbooks that science was done by people who were very smart, who lived alone in the lab and did brilliant experiments and never talked to anyone. And what I learned from working in a lab, even though I wasn't really doing so much science, but just watching how the other scientists spent time talking to each other and discussing their experiments, I learned how social science is and how much it depends on the interactions between scientists. So that was great. At the time, this was also a politically difficult time in the United States. The country had been involved in what I think was an unjust war in Vietnam that should never have been fought, and certainly should not have been pushed to the level that it was fought. And so simultaneous, as a young person, of course, you believe that if you go out on the streets and protest and organize demonstrations and are politically active, that you can change the world. And so as a young person, I believed that, and of course was out on the streets. It wasn't clear to me how that was related to the science that I was doing, and it was like kind of a two-world situation. Either I was in the lab or I was out on the streets.
I think that is quite relevant in our country as well.
Yeah.
A lot of happening.
I think that's true. Just understanding the current political situation in India.
To go in another direction, you have been in research for a long while, and you won the Nobel Prize in '95. So, how have you seen technology impact your field, or to be more, especially computers?
Yeah, and so obviously when I started work, if you said a computer, what someone would think would be a little tiny desk, something about the size of a cell phone that you could add, subtract, multiply, and that was a computer. They were very valuable, and people used to chain them to their desks because they were.
I think they were called the calculating machine.
Calculators, yeah, a calculating machine. The whole field has been transformed by computer and the availability to handle large data, to analyze large data, and in ways that we didn't think. And so that also, the fact that computers allow us to analyze data also has meant that the field has tried to develop experimental techniques that collect more and more data. And so the two things kind of run, in parallel, that because you can handle more data, you collect more data, and you can handle more data, and you collect more data, and so the whole field, I think, is going through a period where rapid technologies are developed that are huge in terms of data and require computer analyses to even recognize what's valuable in the data. And that's very different from an earlier phase where experiments were harder to do, and you would sit down and you would say, what is the relevant thing? What is the question that I would like to answer? What is the specific things that I need to know to be able to answer that question? And then you do that experiment, and you do it with a control, and it's a small amount of data, but chosen data, and you get an answer to the question. I think that was a very powerful approach that has driven all of science up to maybe 1990, right, up to this new period. I think the problem with the new period is that much data is collected because you can, and much of it's cataloged because you can, but the questions are only asked after the fact. And you look at the data there and you try to say, I have all of this data, it must tell me something. What does it has to be useful for something, and then the effort is to find some indications of how biology works from the computational analysis of the data. Now, on the one hand, that's an exciting way of doing it because it forces you out of your preconceptions and forces you out of the models and the simple-minded intuitions that used to drive science. So, in theory, asking a computer something about the data might tell you something different than what you would have asked before.
So you're essentially saying that there's a fundamental change in experimental design.
Right. And so whether it's a fundamental, I see right now it's a conflict, because even though the computers and massive data collection is a new style of science, many of the most important papers and informative papers are still done in the old directed style of thinking, how can I test something, coming up with the single crucial thing, and the experiment and the control that tests an idea and answers a question. And so I think what we're really living in is not in a time of new science, but in a time of conflict between scientific approaches. And I think it will be interesting to see whether that conflict resolves in a new approach that integrates both, or whether the conflict will resolve in a pendulum way where scientists will swing back and forth between the intuitive, directed approach and the large-scale data collection and analysis approach. So I don't know. I think that's an interesting question to predict about the future that we don't know.
Taking a cue from this, what would you say would be the next big thing in biology? Might be the next big thing.
Might be the next big thing. I think the general consensus, there'll be two things. I think from the standpoint of general molecular biology, I think spatial organization at the molecular level, but in terms of the spatial organization of the nucleus, the spatial organization. So we have imaging technologies which are huge data-rich approaches which allow us to have resolution at all different levels. So to understand biochemistry in the context of the cell, you have to put the biochemistry in a spatial pattern. Right. To understand transcription in the nucleus, probably you have to understand the spatial organization of the nucleus. So that's an area where suddenly we combine a new approach to imaging, to a biochemistry, and to a functional analysis at the molecular level. I guess that brings us close to the central question of what is life, which is this organization of process. It's not molecules moving randomly, it is the spatial and temporal organization of molecules that defines how life works. And even though we understand single enzymatic processes, I think to understand life, we have to understand the spatial and temporal progressions and feedback. So I think that's something. I think in terms of areas of molecular biology, or biology in general, obviously many scientists have begun to tackle neurobiology, consciousness, learning, trying to understand it at a cellular level, trying to understand memory. So I think in terms of specific areas, that's an important one. Another important one, I think, is biomechanics, how cells move, how you change shape, how we have ideas there, but we don't have good ways of testing them.
In a sense, it's probably so there was a period of time when science started, it was people doing, there was no distinction between fields.
Yeah.
Now, and as it progressed, then you started having more and more distinctions. People started going more and more technical. And now you have gone so technical that you again need to start.
Right. And it is true, right? If you think back to everything that I said, and all those fields, all those the questions, all those approaches involve computation. They involve quantitative imaging, biophysics, physical measurements, spatial patterns, biological thought, genetics, all that. So I think to be a scientist in the future, a person will either have to become an expert in many different fields, or more likely, develop the skills to interact with other scientists, biologists interacting with physicists in ways where you can have productive research programs, because I think it's probably difficult for anybody in the world to have a truly deep and truly creative understanding of all fields.
Right. Due to lack of time, I'll need to cut my question short. So I'd like to end it with a few words from you for the students here. And for our organization of Campus Radio.
Okay, so I think if the most important thing that I would say to any student here is that your time here is precious. It's a special time. At the university, you have the opportunity to learn things, deep things, learn things that 15, 10 years ago people didn't know. And so you really are here at the forefront of science, and you have that opportunity. It's interesting that you have that opportunity at the age that you are now, because every one of you as students is not yet the person that you will be, and you don't know who you will be. So you're also in this very rich atmosphere of knowledge and thought and discussion. You personally are developing into who you are. And the interaction between learning all those new things and developing personally and learning and getting to know other students who are different than you in some ways, but amazingly similar in other ways, will be a part of your development, both as a person and as a scientist. And so it's a very precious time. And you should maximize everything about it. Maximize the learning of the science, but also maximize your contacts with your fellow students, because you will learn from them as much as you'll learn from your professors.
Thank you. Your words were very insightful and quite inspiring.
Okay,
So,
well, thank you.
Thank you for spending some time with us.
Absolutely. Thank you.